Welcome back to Multivariate Calculus. In this video, we will start our discussion of functions of several variables. As the name suggests, we're going to be taking the idea that we've had throughout our study of calculus, a function of one variable, f of x or r of t, and we'll replace it with a function that takes on several variables, f of x and y, f of x, y, and z. Later on, we will start looking at vector-valued functions of several variables, but for right now, we'll stick with real-valued functions of several variables. So if I get my head out of the way, we can start a little bit more formally. A real-valued function of two variables is any function which we can write as f mapping from r squared to r. And when we're thinking about a function, the first thing you learn to do every time you've been introduced to a new type of function is to start trying to graph them. And for a function of two variables, we're generally going to graph the function z equals f of x and y. So we have two independent variables, x and y, and one dependent variable, z. And the graph of a function in two variables is going to provide us with a surface in three-dimensional space. If we have a function which we can write as z equals some a times x plus b times y plus c, that's going to give us the equation of a plane. We can't get a vertical plane, but we can get a plane in any oblique angle written in this form. We've already discussed planes in some length. I don't feel that we need to do that again. The elliptic parabolas we've talked about before. Z equals x squared over a squared plus y squared over b squared, and we can shift it around and add in some plus h, and it will still give us an elliptic parabola. And likewise, the hyperbolic parabolas. Z equals x squared over a squared minus y squared over b squared. And again, we could shift that up and down if we'd like, and it would still be a hyperbolic parabola. These are functions in two variables that we've already talked about. We've already seen how these graphs work. So I don't feel that we need to think about them any further, at least not for right now. But these certainly aren't the only ways that we can establish a function. So for example, consider the function f of xy equals x over y squared. I'm going to start right away with, let's go into GeoGebra and graph z equals f of x and y. So pretty simply, z equals x over y squared. And we get this surface that, well, it's a little bit hard to follow, but you can kind of look around at it. It's got a pretty hard edge along the y-axis, which makes sense. This function is undefined when y is equal to 0. And this function is 0 when x is equal to 0. So we've got some interesting things that are going to happen. We've got a really sharp bend in the curve, and we can get some idea of how it's structured in a couple of different directions. Although even still, it's kind of hard to see the shape of this graph with just that. So I'm going to follow the same sorts of ideas that we've talked about previously. If I jump back over to my notes, the traces of this curve we can look at z equals f of x and 0, which is unfortunately undefined, so we're not going to get a lot out of that. We can take a look at z equals f of 0 and x. I'm sorry, 0 and y, which just gives us that z is equal to 0 as long as y is non-zero, which is certainly one of the traces, but not all that interesting. The last trace is when z itself is 0, so that's the zeros of the function. F of x and y is equal to 0. Which gives us that x over y squared is equal to 0, which means that x itself is equal to 0. We get just a single point. Or I guess we get a line out of that one as well in the xy plane. When x is equal to 0, in the yz plane, when z is equal to 0, those give us a couple of graphs that we can look at. All right. So to parameterize these, this first one, we set x equal to 0. We let y take on anything it wanted to, and we got out that z is equal to 0. To parameterize this one, we set z equal to 0. We tried to solve for x, excuse me, we tried to solve for y in terms of x or x in terms of y. We got out that x was equal to 0, and we really didn't say anything about y. Right, so those two traces actually turned out to be the same thing. We can put them into our function, but it doesn't gain us all that much. All right, so we graph the curve 0, t, 0, and you can see that, yes, in fact, it is now showing up. It is the y-axis, so we don't gain all that much from it, but it is nice to see that one dividing line, at least to give us some structure for this graph. All right, so that gave us something, but not a lot. So I guess we can turn to some of the other techniques we've talked about before. If I flip back over to my notes screen, the other tool that we used in the past was the level curves. So again, we have that z is equal to x over y squared. That's the function we already know we're dealing with but I didn't have it written down, so now I do. We've already looked at what happens when z is equal to 0. We can try to look at what happens when z is equal to 1. Well, that will give us 1 equals x over y squared, or y squared equals x. We can look at what happens when z is equal to 2, which gives us that 2 is equal to x over y squared, or 2y squared is equal to x. And I'll also look at z equals -1, which gives us that -1 is equal to x over y squared, or the opposite of y squared is equal to x. And once again, we can try to parameterize these curves. So for this curve, we set z equal to 1. We solved for x in terms of y. So the convenient thing is going to be to let y equal t, and then plug that in, we get that x must be t squared. Likewise, we'll end up with 2t squared t2 for this one, and we'll end up with opposite of t squared t -1 over here. And we can plot these curves on our graph as well. Again, the advantage of looking at traces like this is that you can plot these by hand. And get some idea of the feel of what this thing is supposed to look like without having the 3D graph. But even with the 3D graph, looking at the parametric form will help us give some structure. All right, so let's jump back over to GeoGebra, and I'll start putting these curves in as well. A real valued function of 3 variables is any function which maps from R3 into R. And so we're evaluating a function f of x, y, and z, and we'll generally get out another value which we'll call w. Now, dealing with two-dimensional graphs is really easy. Dealing with three-dimensional graphs is tricky, but we can kind of synthesize them on a two-dimensional surface like a screen or a piece of paper. This graph is going to be a four-dimensional shape. And it is well beyond my expectations of this course to show you how to grapple with objects in four-dimensional space. But one of the tools that I will refer you to is the idea of a level surface. So we can look at the graph when w is equal to 0, w is equal to 1, w is equal to 2, and so on. and get a feel for what the level surfaces of the graph are going to look like. Very often, this is impossible to actually do, but if you have a relatively well-behaved function, like f of x, y, and z is equal to x squared plus y squared plus z squared, then when w is equal to 0, we get x squared plus y squared plus z squared equals 0, which is just the point 0, 0, 0. When w is equal to 1, we get the equation x squared plus y squared plus z squared equals 1, which is the sphere or ball of radius 1. When w is equal to 2, we get the ball of radius square root of 2, and so on out that way. So you can look at this, you can graph these, and try to figure out what's going on with the shape that way. Right. The last thing that I want to look at when I'm thinking about a function of several variables is some ideas related to composition. If I have a function f of x and y, and I have another function r of t given as the vector valued function x of t, y of t, then I can take f of r as f of x of t, y of t. And we realize what we've really done here is taken a function of two variables and turned it into a function of one variable. All right. I can't get my computer software to let me draw the picture the way I'd like it to, so I'm going to do my best to draw this by hand. I apologize in advance. All right, but I would like you to imagine that we have some surface z equals f of x and y graphed here in x, y, z space. And then in the xy plane, I have some curve given by r of t. And if I map out a slice straight up from the xy plane into wherever the surface is, and I follow the contours of the surface, then you can think of that as kind of a wrinkled up sheet, right? We take a nice sheet of paper, we bend it so that it follows the path here, the path down here in the xy plane, right? That is a path in the xy plane. So we can think about that and we can just lift straight up along that path and then use the surface up here to slice the top of that sheet. Then I want to take the sheet and stretch it back out. When I do that, I get my t-axis, which is just exactly following this path of the curve. And then I get whatever heights I had mapped out in z. So I just take that sheet, I straighten it out, I see what it comes up with, and that gives me my two-dimensional cut of a three-dimensional graph. All right, so this is the graph of the surface along this path, or the path for this surface. And that's a tool that we're going to use fairly readily throughout our course. Another thing that we might do is to try to follow a change of coordinates. If we have our function f of x and y, and then we redefine x as a function of u and v, and also y as a function of and v, then f of x and y becomes f of x of u and v and y of u and v, which is really just a function in u and v. This is a trick that is incredibly useful in studies of physics. I became something of an expert in working through thinking like this, studying my general physics courses before I was ever exposed to it in a mathematics course. So I suspect many of you are in the same boat. But if I have my x and y axes like this, very often it's useful if I'm trying to describe a system. Say I've got an inclined plane, I've got a mass sitting on that inclined plane, and I'm trying to describe the forces that are acting on this mass, right? We've got a force of friction, we've got a normal force, we've got a gravitational force. To make this thing messy, maybe we've got a spring going on here as well. But in the XY plane, these forces are all kinds of crazy orientations. So let's just create some new coordinates. Let's put a u-axis and a v-axis. The u-axis is parallel to the surface that we are working on. The v-axis is perpendicular to that. And we've moved the center so that it's right there in the middle of the thing that we care about. Now we've got friction in the positive u direction, we've got a spring in the negative u direction, we've got a normal force in the positive v direction, and we've got gravity that's going off at a weird angle. Only one of the four forces is doing anything weird. That's the kind of thing that we're looking at here when we're talking about a change in coordinates. And if we think really carefully about how we change our coordinates, we don't have to stick with a linear sense of it. For example, if we have a function that we care about, f of x and y is equal to e to the x times the natural log of y, we can set up some nonlinear coordinates so that x is equal to the natural log of u and y is equal to e to the v. And with that, we get that f of u and v is actually just u times v, which is much easier to work with in certain circumstances, right? Just doing a substitution. E to the natural log of u is just u, natural log of e to the v is just v. That looks really weird when you try to think about the graph, right? If we think about our normal x and y axes, um, well, if x is the natural log of u, that means that u is e to the x. And so we're going to end up with a new axis that looks like this, and a new axis that looks like that. And it's a very strange way of describing things, but you can still work with it, and that's what really matters. Visualizing the change in coordinates and coming up with the change in coordinates is, well, visualizing is a little bit beyond what I hope you can do this semester. Coming up with them on your own is quite a bit beyond what I hope you can do this semester. But I wanted to lead off with that, thinking about what composition of functions of several variables can mean, so that you have some picture in your mind as we go through and do several compositions of functions of several variables. But for today, I just want to focus on making sure that you're able to graph these. So I'm going to wrap up with one problem for you to try on your own. And it's very simply, I would like you to take a look at the function g of x and y is equal to x squared sine x, I'm sorry, x squared sine y minus y squared cosine x. Okay, that all fit around me. So graph this function, and then looking at the graph, determine which traces or level curves might be convenient, and figure those things out as well. But mostly play around with and get used to the idea of a function of several variables. See what you can do with that, and I'll see you in the next video.